The contents of an executable file may seem like completely chaotic gibberish, but there's a method to the apparent madness. If you know where to look, you can peer into the very destiny of the executable and see all of its potential futures. Welcome to Hello World. In the last episode, we spent a lot of time talking about what a computer was and why they should amaze us. We defined a program as a set of coded instructions and learned about a few different encoding schemes. We also laid out an overview of the subject matter the series plans to cover, so if you'd like to get a sense of that, check out the other episode first. I'll post the link in the description below. We ended that episode with this image, showing a computer program in hexadecimal, often shortened to just hex. I mentioned that each of these blocks represent an instruction to the CPU, but I didn't explain how or why, so let's pick up there. The first thing to know is that the byte I mentioned in the previous episode, 8 binary bits capable of depicting 256 different values, is a concept you're going to hear a lot about in this episode. For the sake of those examples, we have to define our assembly instruction set, or architecture. The CPU at the heart of any given device is generally only capable of understanding a single instruction set. In the case of our Windows examples, it's a set called x86-64. Just like how we showed that ASCII can map numbers to letters, instruction sets map numbers to CPU instructions. You may be rightfully pointing out that those aren't strictly numbers. I mean, after all, there's a few letters mixed in there, right? Well, here's where we bring it back to hexadecimal. Binary is base 2, so a binary digit is either 0 or 1. Decimal is base 10, so a decimal digit is between 0 and 9. But hexadecimal is base 16, so each hex digit is between 0 and F. Yeah, when we run out of numbers, we just switch to letters. 9 is 9, A is 10, B is 11, C is 12, and so on. So, if we go back to our example with the value 203 from the previous episode, we see that we have B plus C times 16, or 11 plus 12 times 16 equals 203. Between binary, decimal, ASCII, and hexadecimal encoding, you've got all the knowledge you need to understand just about any number a modern computer throws at you. I mean, there is also a base 8 system called octal, but it's largely fallen out of favor unless you're changing directory permissions in Unix or directing airplane traffic? If you want to play around with these various encoding types, the calculator program that comes with Windows is actually surprisingly capable. It has a programmer mode you can switch to that will show you values in and perform conversions between any of the numeric codings we've discussed. You too can enjoy the confusion of countless computer science students when you realize how many different ways this number can be interpreted. Don't feel like you have to be able to quickly convert from one encoding to another in your head. I've been programming for years, and it's rare that I need to do conversions. It's much more common that you simply recognize the difference between two numbers, or recognize that the data you're looking at is more meaningful in one encoding compared to another. You will learn to recognize certain magic numbers, though. For example, consider the number 65,535. That may seem like a number I pulled out of thin air, but any programmer is going to immediately recognize that number as the maximum value that a 16-bit integer can contain. There's one last concept we need to cover before we finally understand the cryptic image, and that's file formats. A file format is an agreed-upon structure that ensures interoperability of data between programs. It specifies the types of data it expects and the order in which it expects that data. Just like the binary data in the file can be decoded in different ways, that data, once decoded, can be interpreted in different ways. If you have a sequence of 3 arbitrary numbers, they could be almost anything. XYZ coordinates for a character's position in the video game, RGB values for an image's pixel, amplitude for 3 different audio samples, and so on. If file formats didn't exist, your computer would have no idea what it should do with any of the files you gave it. By convention, certain file formats are associated with specific 3-letter extensions, the letters after the dot in the file name. Why 3 letters? Well, DOS, the operating system that the original Windows sat on top of, used what was called an 8.3 naming convention for files. 8 characters to make a human-readable name for the file, a dot, and an optional 3-letter extension, exe for executables, bat for batch files, txt for text files, and so on. Eventually, Windows outgrew this limitation, but in order to remain backwards compatible, developers mostly kept to the same standard. Although few modern operating systems, if any, require 8.3 or any such short names, old habits die hard, and we're still largely using TLAs to help distinguish file types. As I said, though, the 3-letter extension is just convention. There's something else that determines what a file really is, the file format's header. Headers are a specifically formatted section of data at the beginning of the file that are unique to each file type. You may well rename a file and even change the extension, but the operating system and other programs that open that file will read the header and know what it truly is. We can illustrate this with a console, a glimpse into the operating systems of the past, and something you may never have seen if you're under 30 or don't work in IT. First, let's open a folder in Windows Explorer. In this case, we see 2 files, Hello World exe and Logo PNG. The exe is an executable, a program, and the PNG is an image format. We can double-click either, and they both work as expected. Now, let's rename the files to have different extensions. When we double click on Hello World PNG, it still opens up an image viewer, but it says there's nothing to show. Now let's try the command line. It's much simpler in terms of features, so the only things you can do are type in commands and run executables. Anything you type will be treated as one of those two types. We run an executable by typing its name, so let's just type helloworld.png. Despite the file name, it knows it's an executable and we see the expected output. But when we try and run that image file that we renamed to exe, it knows it's not a valid executable despite the name. So what was Windows doing differently? Well, back in the DOS days, if you wanted to open a file, you had to open a program that could read that file and then use it to open the file. Windows and other GUIs tried to be more convenient by guessing what kind of file you're trying to open and then using some internal map to figure out what program to open it with. When you double-click a file in Windows, it uses the file extension to look up what it should do in order to open it. The console doesn't do that. When you type something in, it first checks to see if it's one of its own internal commands, and if not, it tries to run that file name as an executable. It has no real concept of file formats. It didn't know the image was an image, it just knew that it was not a valid executable by the header. Interestingly enough, the MP3 audio format that we're all well familiar with doesn't have a file header. It has a series of frame headers. Each frame is like a frame of a film, a small part of the whole. It's a format designed to be capable of streaming. We'll cover streaming technology in a later episode, but for now, all you need to know about that is that streaming means that each frame is an independently evaluatable chunk of data. You can start reading from any point in the file or stream and pick up there without too much trouble. What this means in practical terms for the MP3 format is that it needs to be fault tolerant. It does this by discarding any data it doesn't like the shape of and waiting for the next good frame. Now, if we combine these two facts, we can have a little fun making a file that is both an image and an audio file. Let's look at this example I prepared earlier. If we locate combo.png in Windows Explorer and double-click it, it opens up as an image with the show's logo. If we rename it to combo.mp3 and double-click it, it opens up the media player and starts playing the expected audio. Have you ever wondered what really goes on inside a computer? What's going on? Well, Windows determines file type by extension, so it's going to try and open it with whatever program is associated with that extension. Going back to the PNG format from earlier, we know that it has a header that describes the exact amount of data that it expects to find. Trust me on this one. I can go into the details later if you really want me to. We also know that in order to tolerate faults in the data stream due to network issues, MP3 players are willing to discard data that doesn't match its expectations. All we need to do to pull off this trick is to stick the data from an MP3 on the back of a PNG, and this is easy enough to do with the concatenation feature of the console's copy command. That's right, back to the console. There are plenty more tricks that can be used to fool your computer into behaving oddly, both harmless and malicious. If you'd like me to go into more detail on that sort of thing in future episodes, make sure to throw a comment to that effect in below. But that's enough fooling around for now. We finally understand what a program really is. Let's recap. A program is stored in a binary encoded format. If we decode that to hexadecimal, we can examine both the header, which determines what the file really is, and the data it contains. In the next step, we'll finally look at the decoded instructions themselves and see what they do. Bringing back this venerable image, we can see it's an executable. How do we know that? Well, the big giveaway is the first 2 bytes, 4D and 5A, which are going to be the same for almost every executable on a Windows system, because, converted to decimal, they correspond to 77 and 90. When we look those up on the ASCII table from the previous episode, we see they correspond to the capital letters M and Z. These are the initials of Mark Zibikowski. Mark, or Zibo as he was sometimes called, was the programmer at Microsoft who developed the executable file format for DOS. The executable header is far too complicated to go into deeply for now. It takes several episodes on its own. But once you're through the header, subsequent bytes are instructions that we can interpret. In the old days, instructions were laid out in a simple linear format. Start at the start, and follow the instructions in order. In modern systems, the instructions are split up into chunks and spread around the file somewhat arbitrarily. We'll go into more detail on how and why in a later episode. So let's go use some programmery tools to get the assembly instructions, huh? That's what we're here for, right? So here are the instructions those bytes map to. Okay, from one cryptic image to another, right? Stay with me though, we're going to take it one piece at a time. Take a look at the row with the yellow arrow next to it. The first column, 55, is the byte in hex. The second column is the instruction that maps to, in this case, push. Don't worry about what the instructions mean, we'll cover that in the next episode. The third column shows the parameters, the data we need to perform the operation. In this case, it's what we're pushing. The difference between instructions and parameters is very important. If I'm driving somewhere and you tell me to turn, the instruction alone isn't enough. You would need to add the parameter left to let me know which way you want me to turn. Parameters may also be modified by the instruction. If I give you the instruction eat and the parameter burrito, I should make sure I don't later instruct someone else to eat the same burrito, because that's, well, in programming we call that undefined behavior. That mapping from the first column, 55 to push, is defined by the instruction set I mentioned before. If you tried to run this code on a processor with another instruction set like MIPS or ARM, it wouldn't work because the instructions are mapped differently. This is one of the main reasons you can't just copy a Windows executable over to your Android phone and expect it to run. Even if you were able to successfully modify the header to the format needed by the other operating system, the instruction set would be completely wrong. It's possible it would crash your computer, or worse, corrupt vital data. There are programs that can take those alien instructions and convert them to a set that your computer expects, but we'll cover those in a later episode. But wait, does that mean if you want to write an app for iPhone and Android, you have to write it twice? Well, thanks to the magic of high-level programming languages, the answer is mostly no. I'll explain what I mean in the next episode of Hello World.